Hey folks, in this video I want to start talking about how we can actually manage a binary max heap. So we already have this idea, right, of what a max heap is, how it goes together, right, the different rules that kind of apply to it, right, how we can store it, how we can structure it. But we know, right, that at the end of the day what we want to do is we want to use this idea of a heap to implement a priority queue. What this implies is that at some point we're probably going to need to be able to add or remove things. It's going to be a little bit tricky here because if you think about it, we don't really know are we going to add something that's too large or too small. Based on where we put our elements, or remove our elements from, we're probably going to have something that's a little bit out of order, right? And so what we're going to need to talk about in this video and the next is how to deal with that problem. So here what we're going to deal with is basically the issue, right, of adding an element to a tree that is potentially larger than its parent, right? Now we already know that we should have larger things on top. So if we have something that's larger on the bottom, obviously we have a problem. It's no longer a heap, right? What can we do about it? We need to somehow fix it. And so in order to fix it, we're going to introduce this idea of a swim operation. A swim operation is a heap correction mechanism that basically takes a node and moves it upwards into its proper position so that you have a heap at the end of the day, right? Rather than at the beginning you started with something that was slightly out of order, how do we fix that? Overall, the technique is going to be to migrate that node upwards until we get to the appropriate position. So let's take a look at this image here. I have mostly a heap, right? I have the 10, 7, 5, 5. This stuff over here is pretty good in terms of it being a heap. It all obeys the rule of larger thing is on top. But our problem is this node over here. This is clearly out of order. So we would like to fix that. So what we'll do is we'll say we want to swim that node. Swim that node means move it upwards to its appropriate position. So let's look at this here basically as an example to work on the slides, and then we'll go to the next slide which has the actual implementation of the code for it. So I'm looking at this node here, and what I want to do basically is figure out, what should I do? So I need a target, right? So this is basically going to be the node that I want to adjust. And so I'll have to come up with a set of rules to swim it upwards. Looking at this tree, what I can maybe think about doing is basically comparing it with its parent. If it's smaller than its parent, then actually I'm done. I don't need to do anything, right? I don't need to do any swimming operation. It's already where it's supposed to be. But if it's larger than its parent, then I should move it upwards, right? So that could be our first thing, right? Compare with your parent. So I compare these two. 11 is actually greater than 7. So hey, they're out of order. I need to flip them. So then I could basically start to update my tree, right? So we're thinking about just how to fix this, manually, right? If I were doing this by hand, how would this look? So 11, 7 over here, right? That's how it would look. And all of a sudden I'd be looking at, and I'll maybe write my 11 a little bit better. We're now basically going to be looking over here at this node, right? So then the question is, am I where I'm supposed to be, or do I need to be moved again? So again, I'll look at my parent. Oh, hey, I'm still bigger than my parent. That means I need to be flipped, right? So I need to flip with my parent. So this will update, right? I no longer have 11 there, so I have a 10. 11's over here, and this is my current node. Oh, hey, I'm at the end. I can't be pushing any further. I must be where I belong, okay? So that's a pretty simple operation, and that's going to be how our swim works, right? So basically the idea is that if I have a node and I think I need to move it upwards, I'll basically look at that node, compare with its parents. If it's larger than the parent, then swap it. And just repeat this again and again and again until either I'm not larger than the parent or I'm at the root of the tree, right? Those are my two stopping conditions. Okay, given that I follow those two rules, basically I'll be able to fix any node that needs to be moved upwards. Let's take a look at the code for this. So you can see here, right, that I have another example. This is just from the textbook, right? If you want, you can take a look at this. This is another example basically of a node that's out of order, and then we need to basically push it upwards. So I need to push it and push it. Okay. But what about the code? So looking over here at the code, this is our swim method, right? And this isn't for implementing a priority queue yet. Swim is basically a useful method a heap can have to implement a priority queue, right? Obviously, if I have a priority queue, maybe I want to use swim when, for example, adding something new to the priority queue and needing to put it in its proper position, right? Something like that. All right, so I have my swim operation here. So I have basically a loop, right? My loop is going to check to see am I in order or not. Okay, so there's kind of two conditions here, right? So k greater than 1, less k over 2k. So k is basically the node that I'm looking at, right? So I started looking at, in my previous example here, I started looking at the 11, right? That was my arrow there, right? That's basically my k is what that is, right? So going over here, right? K is the thing I'm trying to move up. I have basically my two termination conditions. One is I go outside the tree, right? So that's k greater than 1, right? I should only loop, right, while I'm inside the tree, right? I don't want to be able to push myself back to index 0 or less than 0 or whatever that, right? The smallest index I'm allowed to have is 1, right? So that's one condition there. Second condition is basically see, are you less than your parent, right? And this over here, k over 2, that's coming from the formula we talked about earlier that was used for computing what is the index of a parent node. So this is basically checking to see, are you greater than your parent, right? Or is your parent less than you, right? As how I read this line. So those are the two conditions, and then our code inside is really simple. So if those hold, right, if we're still inside the tree, if we are indeed out of order with our parent, then swap with our parent, right? So exchange those two in the array, and then update my k, right? So I've moved my k upwards, right, with the exchange, and now I need to update k to be a new number that's now the parent of this new position of that node. And so that'll run, and eventually it'll pull my node back up to the top of the tree. All right, so there we go. That's the swim operation. Hopefully you have some sense of what it does conceptually, right? Some sense of the code. Remember that we're not going to use it quite yet, right? We'll need to use it when we implement priority queue. For now, it's just kind of a useful feature to keep our priority queues heap, right, in the proper order, right? The priority queue will then end up calling swim later on when it implements something else. All right, so in the next video, we'll start talking about the opposite operation, which is a sync operation.